Hello guys, today we're going to solve a sample problem in chapter 6 of thermodynamics and heat transfer, the vapor and gas power cycle. The sample problem is a 4-cylinder 2-stroke 2.4-liter diesel engine that operates on an ideal diesel cycle has a compression ratio of 17 and a cut-off ratio of 2.2. Air is at 55 degrees Celsius and 97 kilopascals at the beginning of the compression process. Using the cold air standard assumptions, determine how much power the engine will deliver at 1,500 revolutions per minute. The given values are volume is equals to 2.4 liter, which is it converted into cubic meter that every 1 liter there is 1,000 cubic meter. So 2.4 liter is multiplied to 1,000 cubic meter per 1 liter. Crush out the same units. So we have 0.0024 cubic meter as our new volume. Then we have a compression ratio of 17 and the cut-off ratio which is 2.2. A temperature which is equals to 55 degrees Celsius, which is added to 273, so we have 328 Kelvin as our temperature, and a pressure of 97 kilopascals and a revolution of 1,500 revolution per minute. The cold air standard assumptions are applicable. The kinetic and potential energy changes are negligible, and air is an ideal gas with constant specific heats. So we were going to determine the properties our, of our air at room temperature using our property table. So we have constant pressure equals to 1.005 kilojoule per kilogram Kelvin, and constant volume which is 0.718 kilojoules per kilogram Kelvin, and the gas constant equals to 0.287 kilojoules per kilogram Kelvin, and the specific heat ratio which is equals to 1.4. In process 1 to 2, the isentropic compression, we use the formula temperature at state 2 is equals to temperature at state 1 multiplied to the quotient of volume at state 1 over volume at state 2 raised to the power of specific heat ratio minus 1. Since our process 1 to 2 is isentropic compression, then our volume at state 1 over volume at state 2 is equals to our compression ratio. So plug in the values, we have 328 Kelvin multiplied to 17 raised to the power of 1.4 minus 1 is equals to 1019 Kelvin as our temperature at state 2. In process 2 to 3, pressure is constant heat addition, so we use the equation pressure at state 3 multiplied to volume at state 3. Temperature at state 3 is equals to pressure at state 2 multiplied to volume at state 2 over temperature at state 2. Since we were going to solve for our temperature at state 3, we rearrange the formula. We have temperature at state 3 is equals to volume at state 3 over volume at state 2 multiplied to temperature at state 2. Since volume at state 3 over volume at state 2 is equals to our cut-off compression ratio, so we plug in the values. Now we have 2.2 times 1018.72 Kelvin equals to 2241.18 Kelvin. So this is our temperature at state 3. For the process 3 to 4, isentropic expansion, The formula we were going to use is temperature at state 4 is equals to temperature at state 3 multiplied to volume at state 3 over volume at state 4 raised to the power of our specific heat ratio minus 1. Since our volume at state 3 is over volume at state 4 is equivalent to our cutoff ratio multiplied to our volume at state 2 over volume at state 4. So rearrange the formula. We have temperature at state 3 multiplied to cutoff ratio over the compression ratio raised to power of specific heat ratio minus 1. Then plug in the values. We have 2241.18 Kelvin times 2.2 over 17 raised to the power of 1.4 minus 1 is equals to 989.16 Kelvin as our temperature at state 4. So in finding the mass of our air, we were going to use the formula of our ideal gas, which is PV is equals to MRT. But since the mass is unknown, we rearrange the formula to mass equals pressure at state 1 times volume at state 1 over gas constant times the temperature at state 1. Then plug in the values. We have 97 kilopascals times 0.0024 cubic meter over 0.2870 kilopascals cubic meter per kilogram Kelvin times 328 Kelvin. Cancel out the same units. We have 2.43 times raised to power of negative 3 kilogram or 0.00243 kilogram as the mass of our air. Next, for our heat input, we use the formula mass times the enthalpy at state 3 minus the enthalpy at state 2. Thus, this is equivalent to mass times the specific heat is in constant pressure times the difference between temperature at state 3 and state 2. Plug in the values. We have 2.43 times 10 raised to the power of negative 3 kilogram times 1.005 kilojoule per kilogram Kelvin multiplied to the quantity of 224.18 Kelvin minus 1018.72 Kelvin is equals to 3.038 kilojoules as our heat input. In heat output, given the formula mass multiplied to the difference of our internal energy at state 4 and state 1 is equivalent to mass times specific heat is constant volume times the difference between temperature at state 4 and state 1. Plug in the values. We have 2.43 times 10 raised to the power of negative 3 kilogram times 0.718 kilojoule per kilogram Kelvin multiplied to 989.16 Kelvin minus 328 Kelvin. Cancel out the same units. So our heat output is equals to 1.17 kilojoules. So we were going to solve for our work net output by the formula work net output equals to heat input minus heat output. Plug in the values. We have 3.038 kilojoules minus 1.17 kilojoules, which is equals to 1.868 kilojoules per revolution. Lastly, we were going to solve for the power of our engine by using the formula power output is equals to number of revolution per minute times the work net output. Then plug in the value. We have 1,500 RPM or revolution per minute over 60 revolution per second times 1.868 kilojoule per revolution, then crush out the same units. So we have 46.7 kilojoule per second, in which it is equivalent to 46.7 kilowatts. So that's all for today's video. Thank you for watching, and I hope you've learned something also.